So you can share.
I'll start by sharing my screen. So as Jalal was saying, please don't hesitate to stop me and ask questions.
Oh, and please mute yourself, except for Zaher, of course.
Okay. All right, well, thanks to Jalal for the invitation to speak here and elaborate a little bit on the details of our work jointly with UDank. So, of course, this is a second talk on the subject, so I won't be going into any of the details or background, or I'll just start by stating the main theorem and then going into starting to discuss some of the details that are involved in the proof. I will do the setup and discuss a first part of the proof. The remaining part, which is arguably in a way, heart of the matter, will be discussed by you next week. But I'll point out to it in the course of the talk. Okay, so let me just remind you of the equation that we'll be dealing with. So this is we'll be dealing with the nonlinear Schrodinger equation written over here. And it is, as we said, this is posed on a torus of size L in d dimensions. So this torus is of the form L, a dilation by L of a standard torus 0, gamma 1, 0, gamma 2 up to 0, gamma d. Gamma 1 up to gamma d are the aspect ratios of the torus. The torus is said to be irrational if gamma 1 up to gamma d are rationally independent. This is what that means. And here k is an integer vector, so it's rationally independent if k dot gamma is different from 0. Whenever k is non-zero, is an integer vector that is non-zero. And we say it's generically irrational if, in addition to that, the gamma 1 up to gamma sub d satisfy a Diophantine condition. So this is something from our talk a couple of weeks ago. So the other important parameter of the problem, in addition to the size of the torus L, is the characteristic size of the solutions. So in order to emphasize that, we will adopt the ansatz V equals lambda U, and think of U as having size order of 1 in L2. L2 norm is conserved. Then the equation satisfied by U is essentially the same as that satisfied by V, but there's a lambda squared inside of the nonlinearity. Okay, and here also we rescaled space so that we're working on the square torus of size L, so L01 to the D with periodic boundary conditions, but this comes at the expense of twisting the Laplacian by factors beta 1 up to beta sub d, which are of course related to the factors gamma 1 up to gamma d, the aspect ratio of the torus. So we can think of them as those being the aspect ratios of the torus. And in order to state the results, it is more convenient to state them instead of using lambda as an independent variable. We use this factor alpha, which will stand as the characteristic size of the nonlinearity. So alpha is lambda squared over L to the minus d. So this is just a new variable that is defined in terms of alpha. It's a one-to-one correspondence between the lambdas and alphas. And we'll state the results in terms of the alpha rather than the lambda. So in terms of initial data, we'll take random initial data. We'll take a random distribution of initial data. So this corresponds to taking random and independent Fourier modes. So we expand the initial data in terms of its Fourier series. So here K is in the lattice ZD sub L, which will denote for us the lattice of mesh L inverse. So this is the dual lattice for the torus of size L. And the key point is that we take the initial data to be of the following form. So it's square root of an initial at K multiplied by some random parameter eta K of omega, where eta K are IID random variables that are normalized Gaussian random variables. This is another thing that we pointed out last time, is that we don't really need to take them to be Gaussian. They could be random signs. For example, there's a level of freedom of choosing those IID random variables, but for definiteness and for completeness, we take them to be Gaussians. IID normalized Gaussian random variables. So this will be our notion of well-prepared initial data. So this the reason why this is called well-prepared is because if I take the expected value of U hat initial squared, this is given by an initial of k. So here an initial will be the initial data of the wave kinetic equation, and it will be a Schwartz function on RD. Okay. So as we say here, we can replace those IID random variables by random phases, for example. And the goal of the kinetic theory is to basically to understand the distribution of Fourier modes at later times, or the moduli of the Fourier modes at later time. And here is the central quantity, which is the expected value of U hat of tk squared. And the kinetic dynamics will appear in the limit when L goes to infinity and alpha goes to 0. And this is, as we said, the analog of the Boltzmann theory, where you take the number of particles going to infinity and their radius going to 0. So this is the kinetic conjecture, so I'm using the slides that I used a few weeks ago. So what the kinetic conjecture is, it says it's in the limit as L goes to infinity and alpha goes to 0. So in the limit of large box and weak nonlinearity, the effective dynamics of the moduli of the Fourier modes of NLS is given by the wave kinetic equation, which I will show you or remind you of it on the next slide, rescaled to the kinetic time, which is 1 over alpha squared. So it's for this reason that we introduced this parameter alpha, because in this parameter alpha, the kinetic time scale is 1 over alpha squared, rather than being something like basically L to the 2d over lambda to the 4 in terms of lambda. So it's more convenient to state it in terms of alpha. Okay, so namely what we expect is the expected value of U hat of tk squared is equal to the solution of the wave kinetic equation at time t over t kinetic, rescaled at time t over t kinetic, plus little o of 1. And we expect this to happen in the limit as L goes to infinity and alpha going to 0. Okay. And here's the wave kinetic equation, just a reminder. So this is, it's given by dtn equals k of nn. So this k of nn is a trilinear operator in n, and it has 4 terms that are, so it's an integral over 4 terms. So this is, the first term is n of c1, n of c2, n of c3, minus etc. So these are the 4 terms. And the region of integration is the following. So you integrate over c1 minus c2 plus c3 is equal to c, but you also are integrating over this variety, if you like. It's c1 that is defined by c1 squared minus c2 squared plus c3 squared minus c squared equals to 0. So here again, this is something that I did not define last time, I did not add here. So this is x. When I say absolute value sub beta, we mean that beta sub j x j squared, j being from 1 to d, and this is because we twisted the Laplacian. Okay, so this is the wave analog of the Boltzmann equation. So the one important thing that we discussed last time as well is this notion of scaling law, which tells us in what sense does the 2 limits that are involved in this kinetic derivation are taken. So how do you take the limit L goes to infinity and alpha goes to 0? This is something that was already known to be an important thing in the Boltzmann theory, because the Boltzmann theory is only derived in the scaling law when the number of particles and the radius goes to infinity and the radius goes to 0 according to the so-called Boltzmann grad scaling. Okay, so for us, without discussing that, let me get to the main theorem, which is essentially a proof of this kinetic conjecture. And it says the following. It says if we consider the NLS on the torus TD and dimensions greater than or equal to 3 and with generic aspect ratios beta, we take initial data for the wave kinetic equation to be a Schwartz function. Again, this is something, as we said before, this is an overkill. We just need finitely many Schwartz nodes to be finite. And we take the initial data for NLS to be well prepared. What this means that in the Fourier space, it is given by random Fourier modes, as we have described a couple of slides before. So now we take the scaling law that we adopt is alpha equals L inverse. So alpha goes to 0 like 1 over L when L goes to infinity. And the kinetic time is 1 over alpha squared. The kinetic time is always 1 over alpha squared. It's always 1 over the strength of the nonlinearity squared. But here, since alpha is equal to L inverse, then the kinetic time is L squared. Okay. Then what the theorem says is that there exists a delta, which is a fixed parameter. It's independent of L and alpha, and an absolute constant nu, such that if L is large enough, we have the approximation that we want. The expected value of the modulus squared of the Fourier modes is approximated by the solution of the wave kinetic equation, appropriately rescaled, plus an error that goes to 0 as L goes to infinity. And the key point that this is true for all times between 0 and delta times the kinetic time scale. Okay, so you get to a constant multiple of the kinetic time scale. All right, and the key point, another key remark that I want to emphasize again is that the same results hold for scaling laws of the form alpha equals L to the minus gamma, when gamma is sufficiently close to 1, smaller but sufficiently close to 1. And in that case, we don't need this genericity assumption on the torus. That holds for any shape of the torus that you take, including the rational torus. Okay, so this is the theorem that I would like to discuss today and start setting up its proof and discuss some of the elements of the proof. Okay. All right. So again, please feel free to interrupt me with questions whenever you have any. Okay, so that's all things that we discussed last time. So this time, I will start. This is the official start of today's talk after recalling what we said last time. So we'll talk about 3 setups, structure theorems, and the regular couples. And here's the setup. So this is the equation again. Okay, what rescaled. And this is reminding you of the initial data, or this is the what we call the well-prepared initial data. Okay, so now the first thing that we do is that we do we go from this equation to the Wick ordered equation. So we define the mass. As we said, the mass is conserved for this equation. So we take the integral of u squared. This is the conserved mass. Okay, modulo some maybe L to the minus d factor. Okay, and we define w to be e to the minus I lambda squared m t times u. Then W satisfies the Wick ordered equation, which looks the same as that one, except that you subtract from the nonlinearity this factor 2 times this mass times W. Okay, of course, this does not affect our proof at all, because the expected value of u hat at k squared is equal to the expected value of w hat at k squared. So I might as well prove the result for w for the equation satisfied by w rather than the equation satisfied by u, because they only differ by a phase factor. Okay, and when you take the absolute value, this is gone. All right, and so we will only be interested, or will be only in a way be able to analyze this solution w of t on the interval 0 delta times the kinetic time scale. And remember, we are taking the scaling law alpha equals alpha inverse, so the kinetic time scale is essentially L squared. Okay, so in Fourier space, we go to Fourier space now. We'll try to write the equation for W in Fourier space. But before that, we pull back by the linear flow. Again, this is somewhat of a sort of a simplification so that the equation looks more convenient. So we look at AK of t, which you should think of it as essentially the Fourier modes of W, except that we conjugate them by the linear flow. So this is basically AK of t is the Fourier transform of, we are pulling back by the linear flow. We're pulling W back by the linear flow. And we are another important thing is that this is, we're doing some sort of time rescaling here. So we are taking W hat at delta t kinetic times t. Okay, so that's what we're doing here. So this gives us AK of t. The only thing that you need to remember is that this is essentially the Fourier transform of W hat. And this is the equation that you end up with. So you end up with an infinite system of ODEs for the AK, which is equivalent to, so this is NLS in Fourier space. Okay, most of you are very familiar with this. So this is So here it is dtak is equal to I delta over 2 L to the D minus 1. So the reason why we have this again is because now I'm only analyzing AK on the interval 0, 1. Okay, so we rescale time so that we only need to study AK on the interval 0, 1. Once you study AK on the interval 0, 1, you are studying W on the interval 0 delta times T kinetic. Okay, so this is the cost of rescaling in time and taking into account the scaling law that we're taking, that we adopted, which is alpha equals L inverse. So we have sum over K1 minus K2 plus K3 is equal to K. And we have the restriction that K1 and K3 are never equal to K. And so AK1, AK2 bar, AK3, and we have this oscillatory factor, which comes because we have conjugated back, or we pulled back by the linear flow. Okay, so you see here a factor of delta L squared. Again, this is because we have rescaled time so that we are working on the interval 0, 1 rather than the interval 0 delta times the kinetic time scale. There's an extra factor here that is not very important, and it acts as an error term for most of the argument, which is the case when K1, K2, and K3 are all equal to K. So this is a lower order term that I will neglect for the sake of this presentation. And the initial data is the well-prepared initial data that we talked about. Okay, so omega is the resonance factor. It is given by K1 squared minus K2 squared plus K3 squared minus K squared, which can be written as K1 minus K dot K minus K3. Okay. Any questions for now? So at this point, all I have done is just written the equation, the NLS equation in Fourier space. Okay, that's all we have done, and rescaled the situation so that we are working on the interval 0, 1. Okay, so we only need to analyze this NLS equation on the interval 0, 1. Okay, so the idea is that we had mentioned last time. The idea is to do an expansion of the solution into Picard iterates. So we write AK as AK0 plus AK1 plus AK2, AKN, and then at some point we'll just call the remainder Rn plus 1, for example. Of course, AK0 is nothing but the initial data. So this is given by square root of n initial times those Gaussian factors. AK1 is basically the first iterate of this equation. So you get it by putting inside here AK0. And this is what is written over here, and integrating in time, of course. So here, this is essentially what you get from integrating the right-hand side of the NLS equation and plugging for AK1, AK2, AK3, the initial data. So the way that we would like to look at this is by looking at AK1 even at this point as, and it's with its tree representation. So you have this is K, because you're looking at the first iterate at K, you're looking at the Fourier mode at K, and then we put K1, K2, and K3 here. This K comes with a positive sign. This is positive sign. This is negative. This is positive. So when we are summing over here, we take the sum such that K1 minus K2 plus K3 is equal to K, and this will always be the case when we look at the trees. Okay, and notice that this factor, another thing to notice even from this elementary computation, is that the dependence on time comes in this factor A of T omega, which only comes through omega. So the dependence on time is only dependent on the omega factor, which is defined over here. This is K1 squared minus K2 squared plus K3 squared minus K squared. And this is something that will continue to be hold for the higher iterates. Okay. Here. Now let us look again as a sort of exercise. Let's look at the second iterate. So the second iterate is the sum of 3 ternary trees, basically the ones that are this or this or this. Okay, so here I write for you the expression for this case, in this case. So again, sorry. Again, you just follow the equation. So we have a tree. Now the tree has scale 2. The scale of a tree, if you remember from last time, is the number of branching nodes of the tree. So this is a branching node. This is a branching node. This is over here. This is a tree of scale 1. This is a tree of scale 2 because it has 2 branching nodes. Okay. So so here I'm writing for you a k of t2, where you branch from the second node over here. And again, you have the root. This is the root of the tree. The root is always associated with a frequency k. We will call this a decoration. The precise notion that we use, that we decorate the root by frequency or wave number k. This is k1. This is k2. This is k3. And this is here n1, n2, and n3. And just as at any node, at any branching node, we always have that. For example, at the second branching node, we always have that it is n1 minus n2 plus n3. Okay, and always as well, we have, maybe I'll use a different color. Every node has a sign. So this has plus sign, this plus, minus, plus. That's how we give a signature for the tree. And this is a minus sign. So when the root has, or the branching node has a minus sign, you switch all the signs. So this would be minus, plus, minus. Okay. Another thing to remember is that the end nodes over here, these are called the leaves of the trees, and there will be a distinction between the leaves of the trees and the branching nodes of the trees. Okay, what else can we uncover from this sort of computation? Again, over here, you notice that the dependence on time only comes through the factors omega-1 and omega-2, where omega-1 is the so omega-1 at each branching node, you have omega n equals to kn1 squared minus kn2 squared. Well, I'll state it more general on the next slide. But for example, over here in this case, so here you have omega-1, here you have omega-2, and omega-2 is equal to n1 squared minus n2 squared plus n3 squared minus n squared. I will stop writing the sub beta over here just for ease of notation. Okay, so this is, so each branching node also has associated to it a resonance factor omega-1 and omega-2. So here you have 2 branching nodes, so you have 2 resonance factors. Okay. Here zeta sub 2 is just a product of I or minus I. So here you will have product of I here and minus I coming from here, because the equation itself has an I over here. So that's all that is to it. Okay, so now I can maybe we have built some intuition in order to present the notion, how the nth iterate looks like. So in general, you can easily obtain by induction that the nth iterate is the sum over, so here this is a sum over trees of scale n. So these are trees that have n branching nodes. Let me draw an example here. Okay, this is an example of tree. So the nth iterate is the sum over ak of t. So this is an expression that depends on a tree of scale n. This means that the number of branching nodes in the tree of scale n. And this expression, ak super t, is given as follows. So this is the constant that appeared in the equation. Of course, you raise it to the power n because this involves, you have done n iterates. And then you have a sum over, and again, before I get to that, zeta sub t is a product of factors of plus and minus I. This sum over here is a sum over, over decorations of the tree. So this is the root of the tree. And we know these are the leaves. Okay, so maybe I'll draw the leaves in a different color. So these are the leaves. Okay, so this means leaves. The things in black are the, say, the branching nodes. So these are branching nodes. The set of leaves we will denote it by L. The set of branching nodes we will denote it by script N. Okay. Now, given such a tree, we assign to this tree a set of frequencies. To each node, we assign a frequency k sub n according to a certain rule. And the rule says the following, that the node that is associated with the root is always k. And whenever you have a branching node, you have the property that kn is equal to kn1 minus kn2 plus kn3. Okay, whenever n is a branching node and n1, n2, and n3 are its children. So, for example, if this is n, if this is the node n here, and this is its children n1, n2, and n3, then we must have kn equals to kn1 minus kn2 plus kn3. Okay, and this assignment of wave numbers to a tree is called the decoration of the tree. Okay, so this sum over here, this is a sum over all decorations of the tree. The tree T. Okay, then you have a factor that includes the time dependence, and this factor again depends only on the factors omega n. So these factors omega n for each branching node over here, for example, this is a branching node, then you have an omega n, and this omega n is defined in this line over here. It is given by kn1 squared minus kn2 squared plus kn3 squared minus kn squared. Okay, so for each branching node, we have a factor of this resonance factor omega n. Okay, and then we have the last factor over here comes from the initial data. This is exactly initial data. For each leaf of the tree, there corresponds to, has a copy of the initial data. So we have the initial data, remember, is given by square root of n initial at KL. So this is the decoration of the leaf. So this would be a leaf over here. This is KL. This is the leaf L. Then it has a decoration k sub L. And this is multiplied by the Gaussian factor, the randomness factor, which comes, so here eta plus is eta and eta minus is eta bar because of the signature of the tree. So depending on what is the signature of the leaf. So let us put the signature in a different color. So this has plus, again, this is plus, minus, plus. This is plus, minus, plus. And here, plus, minus, plus. Now this one gets minus, plus, minus. So depending on the sign of the leaf, you put the same sign for the eta over here. So what remains for me is to write for you what this time dependence over here looks like. It's not too hard to write. So it's given as follows. So this A of t omega n is given by the integral over a set delta e to the say pi I delta L squared t omega n, sorry, not t sub n omega n dtn, where delta is the set. So you have tn belongs to 0t for each n in script n. Okay, so this is not, I'm not done with the definition, so let me erase this. So at each branching node, I have a time variable. Okay, let me try to put it in also a different color. So this one has time variable t sub r. If this is called n, there's a time variable here that's called tn, etc. Here you have this is, so for example, this is t2, etc., something like that. Okay, and the relation between these times is the following. So you have that tn is less than tn prime, provided that n is a child of n prime. Okay, so you have a partial ordering over those time variables. So for each, as we said here, just to back up and go a little bit more slowly, for each branching node, you have a time variable in this set delta. And those time variables are all between in the interval 0t. And they are arranged in such a way such that the time variable Tn is less than Tn prime, provided n prime is a child of n. So in this picture that we drew over here, if this thing is n, okay, let's use the same. If this thing over here is n, then and this thing is n prime, then you have that the time variable associated with n prime is less than the time variable associated with n. Okay, and this is just, all this is just by inducting, it's a way to inducting the obvious thing, which is repeating the Picard. It's a way to write the Picard. Okay. All right, so I hope this clarified things a little bit. These are the kind of iterates that we are dealing with. So to summarize, we have the following. We have that the solution is the sum of the first is 0th iterate, first iterate up to nth iterate. The nth iterate is the sum over trees of scale n and of the expression that is given above. So now we start on computing the expected value of ak squared. So if you do expected value of ak squared and you use the expansion above, you will end up with quantities like the expected value of ak of t1, expected value ak of t2. So you have the product of, if you like, two trees, t1 and t2, except that t2 is taken with a conjugate. So we fixed that so that we don't keep on writing conjugates by switching the sign of, turns out that there's a symmetry that if you switch the sign of T2, which means that if I don't start with a plus over here, I start with the minus sign, then this corresponds to taking conjugates. So in effect, what we will be analyzing is the expected value of AK of T1, AK of T2, where T1 and T2 are two trees with opposite signs. Okay, this is because we start with AK of T1, AK of T2 bar. So if you do that, you multiply the two expressions for AK T1, AK T2 that were written on the previous slide. You get the product of the constants, you get the product of the prefactor, and then you have a decoration of T1, a decoration of T2. Remember, a decoration is the assignment of frequencies to each of the nodes of the tree T1 and T2. We have the product of the time factors, A T omega and A T omega for n in N1 and N2. And then we have the product of the contribution of the leaves, which was the thing over here. Okay, so here's the key point, that there's an expectation here. So you have a product of Gaussian. Each leaf gets a Gaussian that is either conjugated or not, depending on the sign of the leaf, and you take the expectation of that. So this expectation is, of course, 0 unless the leaves pair with each other perfectly, and this is a consequence of the independence of the leaves. So here, because we are dealing with Gaussians, we have a simple formula for that. So this is given by Searle's theorem. So if eta k are IID Gaussians, then you have that the expected value of the product of those Gaussian is given as follows. So you basically, you have leaves. Let me try to do a caricature. You have leaves coming from all over those trees, and then maybe from the other tree you have other leaves, etc. What you do is that you do a pairing of those leaves. So you pair each leaf with another. You give each leaf another leaf, which is its pair. Here it's denoted by L prime. Okay, and then you sum over all the pairings. So this expected value is the sum over all the pairings of the leaves, such that the pair is obtained by having one leaf with a positive sign and another leaf with a negative sign. Okay, and this is, and then you equate the decoration of the two leaves that are paired. So if I pair, usually I will denote this pairing by using the same color. So if those two leaves are paired in my decoration, I have to have, and if this leaf is L, this is L prime, I have to have that KL prime is equal to KL. So if I decorate L by K sub L, sorry, then I have to decorate its paired leaf with the same with the same wave number. Okay, so this is something that is also usual in previous treatments of this in this topic. So if we do that, what do we get? We get that this expected value of the product of two trees, if you like, okay, over here, is given as follows. So those are the same as before. Now we have a sum over the pairings of the leaves. So these are, P is a sum over the pairings of the leaves in L1 union L2. So those leaves are paired so that paired leaves have opposite signs. Here, this is a sum over the decoration of, so maybe I can write here, this is a sum over pairings of leaves. This is a sum over decorations of the two trees. This factor B is just the product of the two factors A that are coming from each tree. Two time factors that come from each tree, and then you have that you have a product of n initial of KL, where L ranges over, say, the leaves with positive sign in L1 union L2. Okay. All right, and of course, in the decoration of the trees, something that I missed, we add into the definition of decoration, we add the requirement that two paired leaves have to be decorated by the same frequency or the same wave number, in addition to the previous decoration rules. Okay, so now we introduce a new object, which is a couple, and the couple is a triplet of the two trees, T1, T2, and the pairing. So if we fix the pairing, then we get a couple. We get two trees whose leaves are completely paired to each other. Okay, so a couple are two trees with their leaves paired. We define the scale of the couple to be the total scale of the two trees, so the sum of the scale of the two trees. And a decoration of the couple is a decoration of the two trees, T1 and T2, such that the paired leaves are decorated with the same wave number. Okay, so again, this is what we have done here is just written down the expected value of AK of T1, AK of T2, where AK of T1 and T2 are just the iterates that we discussed before. So here's an example of a couple. These are two trees. Okay, so notice that the leaves of those two trees are completely paired. This red leaf over here is paired with this red leaf over here. So this pairing structure is depicted in this picture using colors. This leaf is paired with this leaf is paired with this leaf, and whenever those two leaves are paired, they have to be assigned the same frequency C. Okay, the root is always assigned the frequency K. Okay, so as a result of this, we can summarize again. So if I'm looking at the expected value of AK, the nth iterate of K squared, then this is the sum over all couples Q of scale 2n, and those couples are obtained. All couples Q were of two trees of scale n. So you take two trees of scale n and you form a couple Q, and this is the same expression that we had before. We derived on the previous slide. We will call this expression for the couple K sub Q. Okay, so what in summary what we have is that the expected value of an squared, the nth iterate, is given the sum over all couples of K sub Q. All right. And one can have similar expressions for the expected value of the nth iterate and the mth iterate. These are also things that are needed in the proof when n is different from n and t is different from s. But I don't write them here for the sake of brevity. So the key point here is that, and this is the central point, is the following. So the number of trees, the number of ternary trees that appear is C to the n. There are only C to the n trees, okay? But if you also assign pairing of the leaves of those trees, then for each such tree, there are n factorial pairings that are admissible for those, if you have a couple of trees whose total scale is n. So what this means is that even though there's an exponential number of trees, the number of couples is factorial. Okay, and throughout this proof, anything that is exponential is harmless, is nice to us. Anything that is factorial is very dangerous. Okay, so this sum over here, you are summing over a factorial number of couples, where if you are looking at sums over couples of scale n, then you have n factorial of such couples. And the key question is, what kind of estimates can we get on this k sub q, okay, this expression over here? All right, so so first of all, we notice that it is enough to look at the so in the proof we will need to estimate the nth iterates, and we will need to estimate the expected value of ak squared. But it turns out that estimated the expected value of the nth iterate squared is enough to get estimates for an by Gaussian hyperconjectivity, which tells you that the size of this is essentially with high probability dictated by the size of its variance. Okay, and this means that we are reduced to obtaining estimates for k sub q and being able to obtain estimates for this and being able to perform this large, factorially large sum. Okay, so here let us do some examples of this expected value of an squared. Of course, the trivial example is the initial data. So this expected value of the initial data is exactly an initial k, which has size order of 1. Now, we can also directly do an explicit computation for the first iterate squared. So if you do the first iterate squared, so this is something that is represented by 2 trees, remember? So the first iterate was represented by 1 tree, and if I take its product with its conjugate, then I have a couple. I would get a couple, and always the roots of the couple are decorated by k. This is k1, k2, and k3. And again, you have the pairing, right? This is paired with this. This will have to be paired with this, for example, and say this will have to be paired with this. There are 2 such choices of pairings, which is why you see a factor of 2 here. So if you do this explicit computation, again, for ak1 squared, you would get this expression, which is exactly the obtained by essentially doing a pair by pair squaring of the iterate ak1 that I wrote for you a few slides before. Okay, so you do that, you do this computation, you get this factor squared, and then you notice that this factor is nothing but sine a constant times omega over omega squared. So if I define this function chi, which is sine pi x over pi x squared, this is an L1 function. This function is an L1, and then I regard this thing. Think of this sine t omega over omega squared. Think of it as a cutoff function. So think of it as you're doing a cutoff to the omega less than 1 over delta L squared. Okay, or more precisely 1 over delta L squared times t. Okay, because that's what you have here. And so by doing dimension counting, the size of this sum is given over here, this thing. So why is it L to the 2d over that? So the reason for that is quite simple if you do dimension counting, although the proof is highly non-trivial. So you're summing k1, k2, and k3. Each one of those is in ZD sub L. And you can think, because these are Schwartz functions, you can think that kj is less than 1. Okay. So in total, this means that you are actually summing only k1 and k2. Once you account for k1 and k2, k3 is fixed by this relation over here. All right, so what is the number of possible choices for k1, k2? The number of possible choices for k1, k2 is L to the 2d, because this is in ZD sub L. So this is a mesh of size L inverse. And there are L to the 2d such k1 and k2. But I have the extra restriction that omega is restricted to a region or a strip which has width 1 over delta L squared t, and this is what accounts to this factor. Okay, so from a heuristic point, the estimate over here can be predicted. Again, the proof of this estimate involves some number theoretic arguments that are highly non-trivial, but the heuristic is fairly straightforward. Okay, so what you get is that this precisely is delta t, okay, the size of AK1 squared. So what this gives is that the first iterate has size, essentially by Gaussian hypercontractivity, the first iterate has size square root of this thing, so the square root of delta t with high probability. So if t is less than if t is less than L to the minus epsilon, if t was tiny, then I would get that the first iterate is bounded by the 0th iterate by a factor of L to the minus epsilon. And in general, I get that the nth iterate is bounded by the n minus first iterate by a factor of L to the minus epsilon. And this is exactly the probabilistic subcritical regime that we dealt with in previous works, So here we want to reach the time t equals to 1. Okay, so here we want to reach t equals to 1 because this is what corresponds to reaching the kinetic timescale. So to derive the wave kinetic equation at the kinetic timescale, we need to reach t equals 1. So this means we only have the best estimate that we could have is that the first iterate is less than square root of delta times the 0th iterate. And more generally, the best estimate that you could hope for is that the nth iterate is less than square root of delta times the n minus first iterate at best. And remember, square root of delta is just an absolute constant in regards to, with respect to the other parameters of the problem matrix. And this is what defines the probabilistically critical regime. So at best, we have the following estimate for the nth iterate. We have at best that the nth iterate is square root of delta to the n. Okay, so here you might stop and ask, well, maybe I could get better estimates. Maybe we can, this is sort of a rough type of argument based on the first iterate. Maybe we can get better estimate, but turns out not to be the case, because if you look at the expected value of the nth iterate squared, then as we said before, this is a sum over couples k sub q, and these couples have scale 2n, and we will see that there are couples, there's a exponentially large family of couples that has size delta to the n. So this estimate over here is really essentially a sharp estimate, okay? And this is exactly generalizes the n equal 1 computation that we did over here, which gave us delta t. Okay, so here we would get delta t to that. And so this is a problem. This is something that we discussed in more vague terms last time, or a few weeks ago when I gave the first talk. So this is a problem because, as we said, there's an exponentially large number of couples of scale 2n. If I look at couples scale 2n, there's n factorial of them. So if I get something that is a factor of delta to the n times n factorial is really brutal. So really we're dead if all the couples, in other words, have this worst case estimate. So our strategy that we also discussed briefly last time is to show the following. To show that for most couples of scale 2n, we have much better estimates than delta to the n. Actually, we get some gain as the power of L to the minus m, where m is sufficiently large. How large it will become a bit more evident on the next slide. And in the worst case possible scenario, we know that there are some couples that have saturate the estimate. We know that there are some couples that have size delta to the n. The best thing we can show, or that's the only thing you can show, is that this happens only for c to the n exponentially many couples rather than factorially many couples. So this is the strategy that we will be following. Okay, so the worst estimates here will be carried by what we call the regular couples that I will describe in a few minutes. And these couples, these are exactly the couples that give you the iterates of the wave kinetic equation, the limit, and the number is indeed exponential enough. All right, so what happens, I'll just have one slide on this and you will elaborate on it next week. So what happens to the non-regular couples, the remaining couples? So for the remaining couples, we would like to define some sort of an index R between 0 and the size of the couple to n, which somehow measures how far these couples are being from regular. So how far these couples are from being regular. So for example, for a couple of index R, and also most importantly, we would like to show the following estimates. We'd like to show that for a couple of index R, we have this following improved estimate. It's not really delta to the n. It's not bounded only by delta to the n, but you get a gain L to the minus CR, where so the gain is comparable to the index of the couple. And the second, more important, probably feature is that the number of couples of index R is only R factorial. Okay, so, and the reason why this is good is that then if you multiply those two things, you would get a acceptable contribution. And here is what I say over here. If you estimate CR factorial by R to the CR, then since R is less than N and N is less than, N over here is always less than some power of log, say log L or log L to the 3, then this is less than log L to the CR, which is much, much less than L to the CR, the gain that I'm getting from the estimate on this couple. So this is really, this is what clinches the argument. This is what closes the argument. So a first candidate for this index R would be the size of the couple that is obtained from Q after you remove all regular subcouples. So what you do is that the first thing you think of, and this is, of course, this is what we thought at first, is that if you start with a couple and you do a surgery in order to remove all regular subcouples, then you would get a couple of size R, and the gain in the estimate for K sub Q would be comparable to the size of this couple. It turns out that this is not the case. Things are a little bit more complicated than that. And the reason for that is that regular couples are not the only ones that almost saturate the bounds, this bound delta to the N. There are two other families of couples, namely what we call irregular chains and type 2 molecular chains. I won't be discussing them or describing them here today because that's not what I will be talking about. But the key point is that once you do this sort of surgery in order to remove such structures from a general couple, then this thing works, this strategy works. The remaining couple or the remaining structure will have size R, which is you can take to be the index of the original couple. And in a way, this is really the most important part of the argument. I won't be discussing it today, but this is partly what you will discuss next time. All right. So just so I know, I started a little bit later, but how much time do I have?
Hey, you still have, I mean, you want, what, 10 minutes is fine?
Yeah, I think I will need just about 10 minutes or less. Yeah. So the next thing that I want to discuss are regular couples. So these are the couples that we said saturate the estimates in our proof. So, and the importance of those regular couples can be seen at the level of the iterates of the first iterate, from the first iterate, or at the level of all the first iterate of the equation. So remember, again, we go back to the computation, to the explicit computation that we did, which is the expected value of AK1 squared. We obtained this quantity when we did this explicit computation. And again, we said you can regard this quantity over here as an approximation of identity. So think of this as chi 1 over epsilon, chi of omega over epsilon. Okay, so you take the epsilon, actually it's epsilon times 1 over epsilon, chi of omega over epsilon, where chi is given over here, and epsilon is, what is epsilon? 1 over delta L squared. T. Okay. And if you do the, since L is going to infinity, if you do this approximation of identity, although this is from a rigorous point of view, this is far from being as easy as a usual approximation of identity, because this is this omega is not this is a nonlinear factor, this omega over here. But let us pretend, let's neglect this this complication over here. And if we think of this as an approximation of identity, then as epsilon goes to 0 or as L goes to infinity, then you get a delta function in the omega. This is where you get the delta function in the wave kinetic equation. And you get the first iterate, essentially, of the wave kinetic equation. You get T times the first iterate of the wave kinetic equation. Or actually, it is not the full first iterate of the wave kinetic equation. This is part of the first iterate of the wave kinetic equation. Remember, the wave kinetic equation, if we can go back, maybe, has 4 terms in it. So that I have over here. So this is, there are 4 terms corresponding to this, this, and this. Okay, so what we have recovered now is the term that is the last one, which concerns this cancellation. So we have obtained n of t1, n of t2, n of t3. So we've obtained only one part of the first iterate. So let's see where the other part is. Okay, and this part, by the way, before I move on to discussing where the other part is, this part comes from the following couples. So this is something that I drew before. This is in the first iterate, you have a tree of scale 1 coupled with this tree of scale 1. Okay, and you have this is paired with this is paired with this is paired with this. Okay, or you might have the opposite ordering over here. So there are two possible choices. We call those 1-1 mini couples. Okay, so these are, because this is a couple of scale 1, this is a couple of scale 1, so these are 1-1 mini couples. Okay. Okay, so now I can tell you where the rest of the first iterate of the wave kinetic equation is. The rest of the first iterate comes from taking the expected value of the 0th iterate with the second iterate, okay, or the conjugate of that. And these are represented by pairing the following trees over here with a trivial tree with one node. So you pair this, I'll draw it in black. If you pair this with this, so this, okay, this is a couple that gives you one of the iterates of one of the remaining parts of the first iterate of the wave kinetic equation. Okay, so these are trees that have a very interesting and very precise structure. So they are trees of scale 2. There are 2 branching nodes. And what you do is that you pair the leaves upstairs with 2 of the leaves downstairs in all cases. Okay, and then there are 6 choices of them. We call these trees the mini trees. And the couple that is obtained by pairing this mini tree with the trivial tree, or which is the single node, we call that a 2-0 mini couple. This is to be compared with the 1-1 mini couple, where you have 2 trees of scale 1 that are paired. Okay, so this will be the, as we said, all the first iterate of the wave kinetic equation is obtained only from those couples, those mini couples. Okay, so this is the mini couples by themselves give you the first iterate of the wave kinetic equation. And as such, if you want to build the remaining iterates of the wave kinetic equation, they have to be coming from couples that are obtained only by using those mini couples as building blocks. They cannot come from arbitrary couples. They have to be coming from the couples that are obtained from using those as building blocks. And this is exactly what we call the regular couples. So regular couples are exactly the couples that are built using mini couples as building blocks, according to a recipe that I will tell you in the next slide. Okay, so these are, if you like, they become sort of the atoms of your couple, and then you only use those structures in order to build a bigger couple. So here's the precise definition of a regular couple. It goes as follows. So of course, the trivial couple, which is formed by just 2 nodes paired to each other, is a regular couple. And then, so this is the base case. This establishes the base case. Now, given a regular couple of scale n, here's how you can obtain regular couples, all regular couples of scale n plus 2. So they are obtained by doing one of the following 2 operations. Operation A corresponds to, you take 2 leaves, 2 paired leaves in the couple Q. Okay, so this couple Q has, if it has scale n, then it has n pairs of leaves. You take 2 paired leaves, and then you extend the couple as follows. So you basically attach a 1-1 mini couple at those paired leaves. So I do this at each paired leaf, and then I pair this with this, this with this, this with this. Okay, this is exactly what is written in this picture. Okay, so this is one operation. The other operation is the following: you take any node in this couple Q, so and you replace this node by a mini tree. So one of those 6 things that are seen drawn over here. So you replace this node by a mini tree, and then you attach whatever is attached to the top of this node at the top node here, whatever is attached below it to the node over here. Okay, and this gives you all the regular couples. So as such, the way they are defined over here, all regular couples have an even scale, and they actually turn out to saturate the couple estimates mentioned before, and actually their estimate is around delta to the n. Okay. Again, not all, as we said, those regular couples are the ones that are the candidates to give you the iterates of the wave kinetic equation, but it turns out that not all regular couples converge to iterates of the wave kinetic equation. Only a subfamily of them does. These are called dominant couples. So this is a subfamily of the regular couples. And all the non-dominant couples somehow cancel in a very nice way, either cancel together or they vanish in the limit. And the only thing that you are left with is the contribution of the dominant couples which converge to the iterates of the wave kinetic equation. So, so this is obtained by doing an analysis of those regular couples, which I will discuss briefly over here. So the analysis of the first step in the analysis of the regular couples is a structure theorem for those couples. And here's the structure theorem that I will describe on this slide over here. So what the structure theorem says the following. So there are any regular couple can be written in the following two ways. The first way is that it could be of this form. So this is T1 plus, T2 minus, T2 minus, T2 plus, and maybe I'll use a different color. And then a T3 plus, T3 minus. So these are the roots. So this couple can have the following form.
Zaher, question.
Yeah.
Did you write T1 minus instead of T2 minus?
Yes, this is T1 minus. Yes, thank you. Where each Tj plus Tj minus is a regular couple. Okay, so this structure theorem allows you to basically do an effective induction process in order to analyze those regular couples. So any regular couple is obtained. So this is one case, this is case A, and then there's case B. Okay, so here what case A is saying is that it has the following form. This is the root, and the first child of the root, at this child you have attached a 3T1 plus, and at the first child of the other one you have T1 minus, such that T1 plus, T1 minus form a regular couple themselves. And the same thing happens for the other two nodes. The other possibility is a little bit more complicated. Actually, it's substantially more complicated. So what you do is that first you use the mini trees that we talked about to obtain a chain of mini trees, actually two chains of mini trees, something like that, maybe like this. And let's say I'll just simplify my life over here. And then remember in the mini tree you had something like this paired with this, and this paired with this, where those are nodes. And the same thing, for example, this paired with this, and this paired with this. Okay, so the same thing, it's as if, so we call those, these are two chains of mini trees, we call those a regular double chain. Okay, and then if I wanted to continue the pairing over here, you might have something that this is paired with this, this is paired with this, and what else? No, sorry, it has, I drew something, an extra thing. So this is paired, this is paired with this, and this thing is paired with this thing, and then what remains is, what is the color that I haven't used? Maybe this paired would be paired with this. So this would be a regular chain. This is something that I constructed by only using the mini trees that I talked about. Now, except as having those as just nodes, each one of those becomes the two edges of a regular couple, just like over here. Okay, so for example, this and this are the two trees of a regular couple. So plus, minus. And of course, the regular couples that fit here, here, here have a scale that is strictly less than the big regular couple that contains them. And this is what allows us to do an effective induction process. Okay, so that's a quick way to explain the structure theorem of those regular couples. And then the key point, or the first key point, is to analyze the time. So as we said, in the expression k sub q, there's always a function that depends on time, but this dependence on time only comes through the factors, the resonance factors omega n. Okay. Now for regular couples, for each omega n, comes in a copy. So there are 2 copies of each omega n in the regular couple. So if you see omega n at one of the nodes, there must be a minus omega n at another node. And this is what allows us to compute this essentially explicitly, and compute this k sub q explicitly for the regular couples, the structure theorem and those properties. So if you can change variables so that you make each omega n of the form x dot y, where x and y are in ZD. So what turns out, I know I'm out of time, so I'll go quickly. So this time function, this b function, becomes a function b tilde of x1 dot y1 up to xn dot yn, and each of those resonant factors is preceded by delta L squared. Again, you think of this as an approximation of identity in higher dimensions and in a nonlinear way. Okay, so you have sort of, again, you have a structure of the form, you try to write it as a structure as 1 over epsilon chi of x1 dot y1 over epsilon, where epsilon is delta L squared here. Again, the proof of this is highly non-trivial. It's a full section in the paper. You need to use the Hardy-Littlewood circle method in order to justify that. But in the limit, what you get is what you get in an approximation of identity. You get the L1 norm of the cutoff, this b tilde, multiplied by this integral, which starts looking like a higher iterate of the wave kinetic equation. So it involves delta functions of omega j. Again, this is things are even more complicated than that. It turns out that this function b tilde is not always in L1 in all its variables, but the good thing is that if it's not in L1, then it takes a very simple structure. It's of the form 1 over principal value in the variables in which it fails to be in L1, and these instances cancel out in the limit. Okay, this analysis is done in section 5 of our paper. The large box approximation, as I said, is based on a number theoretic argument, which is the Hardy-Littlewood circle method. This is section 6 of the paper. And then after this large box approximation is done, one obtains the cancellation of all non-dominant regular couples, and you're only left with dominant regular couples. And for those dominant regular couples, you can match them precisely to the iterates of the wave kinetic equation. I won't explain that. This is the section 7 of the paper. And in effect, what we get is the following proposition, is that if you look at the contribution of all regular couples of scale to n, this is k sub q of tk, you sum over all regular couples of scale to n. Remember, this is still an exponentially large sum. Then this can be compared with the nth iterate of the wave kinetic equation, and the difference is in some norm, it is negligible in the limit as L equals to infinity. All right, so that's all from me today. The remainder of the story, or part of the remainder of the story, will be covered by you next week.
Thanks, Zaher.
Thank
you. Any questions before hang up? If no, I have a small question. Can you remind me why is there only exponentially many regular couples?
Oh, that's a non-trivial thing, actually, and it follows from the structure theorem of the regular couples. It's not a very hard thing. It follows from you write a generating function, and then you get a recursive form for the generating function, and you get that there are exponentially many of them. So it's something that follows from, it's a non-trivial property, but it's something that follows from the structure theorem, from the structure theorem of regular couples.
Okay, and where is it in the paper, if you can remember?
Maybe before section 5, I think maybe section 4.
Maybe we can talk about this later.
Yeah.
Late. Okay, any other questions do we have here? Okay, so thanks, Zaher. And next week is going to be you, to tell us a little bit more, and see you next week. Thanks, everyone.
Thank you.
Thanks again. Take care.